Hello class, today we're on lesson number 6 on chapter 9. We're going to be squaring binomials, okay? And we have a photograph here of human chromosomes. One of these chromosomes contains the gene for eye color. Now, if we go down here and we start reading, we're going to read that the color of a person's eyes is determined by a pair of genes inherited from his or her parents. For simplicity, we will assume that these genes are of two types, one corresponding to blue eyes and the other to brown. The gene for brown eyes is dominant, so a person who inherits one of each type has brown eyes. Now, if 60% of the eye color genes in the human population are for blue eyes and 40% are for brown eyes, what percentage of the population will have eyes of one color, of each color, excuse me? One way to solve this problem is with a diagram. If 60% of the genes are for blue eyes, 6 out of every 10 mothers will pass on the gene for blue eyes, as will 6 out of every 10 fathers. The diagram at the top of the next page shows the outcome of 100 births. We have 36 children, each indicated by this circle. It's a white circle. You know, it's not filled in, and we will inherit. These will inherit a gene for blue eyes from each parent, and will, as a result, have blue eyes. So if we look at the top of the page, we see 6 multiplied by 6. All right, we can go ahead and just put that up here on the board. Create a little box over here. And we'll make it so it kind of gives you an idea of the same proportion. You see the larger boxes to the left and to the top. And so we have these numbers, and we have 6 being multiplied by 6. So now these are the blue, okay? And that would give us 36 here, okay? Or as you can see, they use 6 squared, okay? There's a 6 squared, right? Now, we also have, if we continue reading, as a result, they would have blue eyes. Now, because the gene for brown eyes is dominant, the 48 children, each indicated by the half circle, the half solid circle, all right, who inherit a gene for the blue eyes from one parent and a gene from the brown eyes the other. They will have brown eyes. Now notice those are here. You have a 4. This is 4 out of 10. And so these would each have blue and brown. So remember the 6 is the blue. Blue times blue is going to yield blue. But blue times brown is going to give us 24. And blue times brown here will give us 24. Okay. All right. Now what do we have? Well, we have these two. That would be 48. We would add these two together, and that would give us 48 of these types. So of the we have the blank circle, let's call it. That would be 6 times 6, so we have 36 of these. Now the half solid circle looks something like the way they did it. All right, and that's going to be 48. And then lastly, the 16 children, each indicated by the solid circle. Last time we did these were for the number trick, right? Yeah, I'm sure you don't want to do those anymore. And that would be 4 times 4, that would give us 16. Okay, 4 times 4, that would be 16 here. So if you look at the chart, you can kind of get a better picture of it, and you can see how they indicated each individual child. And they receive a gene of the brown eyes from each parent. So they'll all have brown eyes. So here we have blue, because it's blue and blue, but blue and brown will yield brown. And brown will yield brown. Okay, oops. Sorry, that's brown. And So 36% of the population will have blue eyes and 64% will have brown eyes, because we would add these two together. These two would be 64. So 36, and again, this would be the percentages. We have 10 times 10, which would yield 100, right? So we have 36 out of 100 would be 36%, and 64 out of 100 would be 64%. Okay. Now it is evident from the diagram. Now let's take a look here. We were multiplying 6 plus 4 on each side, right? If we were going back to our thinking where we had a box and we have 6 plus 4 times 6 plus 4, and we're multiplying, so that would be 6 plus 4 squared, wouldn't it? Okay? And if we did that, well, what are we going to get? We're going to get 6. We had 6 squared over here. I'm sorry, I didn't put the 4 squared in here. What do we have? We have 6 squared, which was 36, plus we had 6 times 4, but we had it twice, didn't we? We had 6 times 4 and 6 times 4. We add them together, so we can say 2 times 6 times 4, as they are indicating. And that 4 just looks a little funny, so let's fix it. Okay. So we have 6 times 4, and then we're going to add 4 squared, because we squared the 4 here. So we have 4 squared. Okay. Now, if we were to replace 6 and 4 with variables like x and y, okay, let's do that. So we have x plus y. What would that mean? And we're going to square it. Well, we would have the first term, which was the 6, is now x. We could then say that's x squared, right? All right, we're just simply replacing the number with a variable. But we're going to see that we can do the same math here. Then we have plus 2 times, because remember there's going to be 2 of these, 2 times x times y, or 2xy. We're substituting the x for 6, and we're substituting the y for 4, so it would be 2xy. And then lastly, we would have the y, which we have squared. Remember, we did that up here with the 4, so we have y squared. So we can say that whenever we have a binomial x plus y, we know that you can simply square the first term, that would be x squared, multiply the two terms, and then multiply that by 2. So we have x times y times 2, 2xy, and then square the last term, y squared. Okay. Now let's continue reading here. A polynomial that contains 2 terms is called a binomial, and one that contains 3 terms is a trinomial. We can understand the bi meaning 2 and the tri meaning 3, right? Like a bicycle having 2 wheels and a tricycle having 3. All right, the preceding equation shows that the square of a binomial, x plus y, is a trinomial, x squared plus 2xy plus y squared. Now here are some more examples. We have 2 more examples, and we see here that, and we have the box over here to the right, by the way. I should indicate that we have the box. We have x squared, we have the xy, and the y squared. Okay, so we can see how this works in both methods, multiplying them if we did the FOIL method or we decided to do this. Now remember, when we're saying FOIL method, you might say, well, I don't see 2 terms here being multiplied. Or I'm sorry, 2 binomials, but they actually are. Remember, they're being squared. So we could have written this as 6 plus 4 times 6 plus 4, which is basically what we did up here, and we could have done x plus y times x plus y in parentheses, right? So the square basically means that we're multiplying something by itself, and these happen to be binomials. So now let's take a look. It says find the square of 25 by squaring the sum of 20 plus 5. So what did they do? Then the square of 25, which would be 25 squared, okay, that would be 25 times 25. Well, they're going to break it apart into 20 plus 5, which is the same thing. We've already learned that. And we can see here using both the method going across and using the box. We have 20 times 20, which is 20 squared. We have 20 times 5, and we multiply them each twice. So we have 2 times 20 plus 5, or we have 20 times, or 2 times 20 times 5. And then we add 5 squared at the end, and when we add it all up, it's going to add up to 625. And if you were to take your calculator or just multiply it on the side, 25 times 25, you'll see that it's 625. Okay, now let's clear up our board here. Hold on one moment. And let's continue on with our second example. We have here on the top of page 424, we have the square of x plus 7. So what do? Well, they're going to go x and 7 on each side of the box. They're going to multiply each. We have x squared. Notice we have 7x, and it repeats again, 7x. And as we would look over here to the left, we could see they're going across, and they're simply going to take x squared, and they're going to multiply 2 times 7x, or 7 times x, or x times 7. Remember, those are the two terms. And then again, we have a 7 squared at the end. So you could see how this is similar no matter what numbers, what variables we have. We will always have the squared in the top left corner. We will have a square in the bottom right hand corner, and then we would have the two like terms in the opposite top upper right hand corner and the lower left hand corner. So as we can see, like the x squared and the 7 squared, and then we have the 7x and the 7x, and we just multiply the 7x times 2, which is again like adding 7x plus 7x. Now notice this is simply when we are squaring a binomial. Must be very careful. We don't just start applying this to everything. We are particularly dealing with squaring a binomial. Now, in each of these examples concerning squaring a binomial, that is the sum of two terms. We see that we have a diagram below that illustrates what happens when a binomial that is the difference of two terms is squared. Now let's go ahead and take a look at that, because we can have the sum and then we have the difference, and the difference would obviously mean they're being subtracted. So it's going to be very similar. The only thing is that we're going to be dealing with a negative here. So in dealing with the negative, we must be very careful always, right? Get my pen here. Let's go ahead and write this out. I'm going to go to the right this time and write x minus y squared. So what would we have? We have an x and a negative y, and then we have an x and a negative y, right? So what happens here? Well, we're going to multiply x times x, and we'll get x squared. We're going to multiply x times negative y, would give me negative xy. Then we'd have positive x times negative y. Again, we have negative xy. And then we have negative y times negative y, which yield a positive, right? And that would be y squared. So what can we say here? Well, we're going to end up with x squared. We're going to add these two together, which gives us a negative 2xy, very similar to the other one that we had, and then plus y squared. So we see the difference here is that when we had addition, and I'm sorry, I forgot the y, we ended up with all positive terms, right? Plus 2xy plus y squared. And in this case, we have a negative, so the negative fits neatly in here. So we would, when we have this, and these are forms because x and y could actually be other things. It could be different variables. We can have x might be x to the third power, and y could be 3. Okay. So, or it could be a variable as well. So these are forms, and if you kind of remember the form and you know what you're doing with each term, this is a nice little shortcut. In fact, when we start doing factoring, we're going to need to recognize these opportunities to say, oh, that's a square of the two terms. The question is it addition? Is it subtraction? And you'll notice that primarily right here. If you see a negative term, then you know they're subtracting, and if you see a positive term, you know they're being added. But the question is, can we see the first term being squared? Can we see the second term being squared? And do we see the two terms multiplied together times 2 in the middle? That's what we're going to be looking for. Okay. Now, they show us an example here. Find the square of 99. Okay, by squaring the difference of 100 minus 1. Now, when we talk about the square of 99, we say 99 could be represented as 100 minus 1, right? Okay, so we're just taking 99 and squaring it, but we're going to do it using a binomial, and we could use 100 minus 1 as a way of expressing 99, and you can see that you end up with 100 squared, right? We're squaring the first term. The second term, we multiply. Negative 1 times 100 times 2. So we would have negative 2 times 100, and I'm going to put times 1 here because I already put the negative here. Okay, I could say plus and then negative 1 here, but I'm just going to, it's only one negative, so we know this is going, the answer is going to be negative. Okay, and then we're going to add negative 1 times negative 1, or it would be positive 1 squared, which we know is 1. So when we do our math here, 100 times 100 is going to be 10,000, and then minus 200, which would be negative 2 times 100 times 1, plus 1. And when we do all of our math here, this would equal to, that would be 10,000 minus 200, that's 9,080, or 9,800 plus 1, so it's 9,801. And if you took 99 and multiply it times 99, this would be your answer. Okay, so kind of shows you how this really works. Okay, let's take a look now at the example. We have example number 4. We have 3x minus 5. Okay, so if we square it, we can see here the same result. We're going to take the 3x and we're going to square it. Then we're going to take negative 5 times, or positive 3x times negative 5 times 2. So we'll represent it. We know it's going to be a negative because one of those three is negative. So it'll be negative 2 times 3x times 5. And then we're going to square the negative 5, and again, anytime you multiply something, negative times negative yields a positive, so we have 5 squared, all right, plus 5 squared, and then again, we'll see the answer here is 9x squared minus 30x, because we have 2 times 3 would be 6, times 5 would be 30, so it's negative 30x, or minus 30x plus 25. Now, so we see these two patterns here. We have x plus y being squared, all right, in parentheses, and we also have x minus y in parentheses being squared. And we can see that just the xy term in the middle is going to either be positive or negative. We square each of the terms, then we multiply the two terms and multiply them together, multiply them each, then we multiply by 2 because we see that in the boxes we end up with 2 of these when we're doing this chart or this box method that we use. Then we square the last term. So we can kind of visually see this. We have it here right in front of us over here, right? The square, the 2 times, and then the square. Now, what happens when we have one positive and one being added, one being subtracted? This is a neat one because what happens, let's clear up the board here. Okay, so we have two terms. One is a sum and one is a difference. Okay, when we have a sum and a difference, okay, we had a sum in the first one being squared, and then we had a difference being squared. But now, what if one is a sum and the other one's a difference? Okay, I like this one. This one's really neat. It's called the product of the sum and difference of two terms. Okay, so notice that we're dealing with two terms, x and y, but in one case they're being added, in the other case they're being subtracted. And again, I love this one. This is my favorite one because something special happens here. And it really makes math so much easier when you can understand when you recognize these patterns, and what we get is, well, we have, well, I'm sorry, before we do that, let's go ahead and put it into our boxes here. We have an x and a negative y, and then we have a positive x and a positive y. Okay, so one's positive, one's negative, because we have a sum and a difference. So we have x squared, x times x, then we have x times negative y is negative xy, and then we have x times y, which is positive xy, which gives us a great opportunity here. Now we also have y times y, that would be negative y squared. So, well, what do we have here? Well, we have a really unique opportunity. I say unique. Won't be so unique if they show you a lot of these, but I like it compared to the others. We don't have the same opportunity others, that we see that one's going to be positive and negative, which actually means they cancel out. Okay, so we have x minus y and x plus y, and we can actually express these by canceling these out and simply dealing with the x squared minus y squared. Okay, so when we see x squared minus y squared, we can actually write them, or write any term that we have that's being squared. So you have two terms that are being squared and they're being subtracted. We can factor them out to be x plus y times x minus y. And I use x because that's the example we're using. This is sort of the form. But we will recognize opportunities. And you may see, and I'm going to go to example number 5. And when we start dealing with these types of problems in the factoring side, I want to show you sort of a backward method, which is really used for factoring. Okay, so we're just going to get rid of all these guys. Now I'm going to keep this here, and now we're given find the product of 4x plus 9 and 4x minus 9. Now according to this, we should be able to, we have 4x plus 9, and then we have 4x minus 9. So we should just be able to square 4x. Right? Now notice it's 4x, all of it's being squared, okay? Not just the x, okay? And it's very important. We know that the law of exponents are going to require that we apply this squared to both of these factors, right? And then we're going to subtract and do the same here for the 9 and square it, okay? And what do we get? Well, we have 4 squared would be 16. And x squared, well, is x squared, right? So we squared the 4 and we squared the 16. And then 9 squared is 81. Okay? Now, when I said about the backward method, I was saying, well, I was actually referring to factoring. I want you to be able to see here that we have some squares, some perfect squares. Right? The perfect squares, there are actually 3 going on here because we do have this coefficient hanging out here. Now we know 81 is a perfect square because that's 9 times 9, right? So that would be 9 squared. And we're subtracting here, okay? And we have also 16 as a perfect square, all right? That would be 4, and x is a perfect square because that's x times x. So we can kind of go backwards with this. And we could see how we go from one to the other. We can sort of factor it backwards. We have the 4 being squared, the x being squared, and the 81. And being that we have this minus here, that's the key, okay? Because if this were plus, we wouldn't be able to do this. We would then be able to say, well, I could take the first term that's being squared and say that is 4x. And I could take the second term as 9 and say, this is the product of the sum and the difference of these two. Now notice it has to be the sum and the difference. Do not think that we could do this because we already know that when we have x plus y being squared, Please do not assume that this is x squared plus y squared. We know that that's not the case, right? Because you'd have to also multiply x times y multiplied by 2, right? So we couldn't do that. Always notice that when we have this opportunity, there has to be that negative in between. And don't assume when you see x squared minus y squared, oh, well, that should just be x minus y squared, because it is not. We see that it's actually x plus y times x minus y. So when you see this opportunity, again here, we have perfect squares all abounding. We can start factoring backwards. So that's kind of peeking into the future, let's just say. So let's just finish up here. It says, we have considered the following three patterns in this lesson. We have the square of the sum of two terms. So we have parentheses x plus y and parentheses raised to the second power, and that's going to be x squared plus 2xy minus y squared. We also squared the difference of two terms. We have x minus y squared, and we end up with, again, the 2xy term becomes negative, and so that would be x squared minus 2xy plus y squared. And then lastly, we covered the product of the sum and difference of two terms, x plus y times x minus y. These are all in parentheses, and that will equal to x squared minus y squared. Now, although these patterns are merely special cases of multiplication, they are frequently found in algebra, and they should be remembered, okay? And you'll see further on when we start factoring and we get into factoring, we're going to be rushing into that pretty soon, okay? That will be chapter 10. We're going to be challenged to remember these three in particular. So just get familiar with them, understand the form that we have here, and then try to apply that form to the terms. That's going to be the tricky part. Being able to find those perfect squares. So as I say, it's 16x squared, okay? Now, if it said 9x squared, again, 9 is a perfect square. That's 3 times 3. Now, if I said 24, you wouldn't really have a perfect square, but 25 would be 5 times 5, but 24 would be 6 times 4, so that wouldn't necessarily work. So, so that is the end of lesson number 6.